What is pipelining? Pipelining, a standard feature in RISC processors, is much like an assembly line. Because the processor works on different steps of the instruction simultaneously, more instructions can be executed in a shorter period of time. To demonstrate, we use the laundry analogy. Let's say there are 4 loads of dirty laundry that need to be washed, dried, and folded. We could put the first load into the washer for 30 minutes, dry it for 40 minutes, and then take 20 minutes to fold the clothes. Then pick up the second load, wash, dry, and fold, and repeat for the third and fourth loads. Supposing we start at 6 pm and worked as efficiently as possible, we would still be doing laundry until midnight. However, a better approach to the problem would be to put the second load of the dirty laundry into the washer after the first was already clean and whirling happily into the dryer. Then, while the first load was being folded, the second load would dry and the third load would be already added to the pipeline of laundry. Using this method, the laundry would be finished by 9:30. Without pipelining, here's what the MIPS architecture looks like. Instruction fetch. The instruction is fetched from memory and placed in the instruction register. Instruction decode. The bits of the instruction are decoded into control signals. Operands are moved from registers or immediate fields to working registers. For branch instructions, the branch condition is tested and the branch address computed. Execution. The instruction is executed. Specifically, if the instruction is an arithmetic or logical operation, its results are computed. If it is a load store instruction, the address is computed. Memory read or write. If the instruction is a load store, the memory is read or written. Write back. The results of the operation are written to the destination register. This is the basic pipeline of MIPS architecture.
What are pipelining hazards? As we all know, the CPU speed is limited by memory. There's one more case to consider, that is, a few instructions are at some stage of execution in a pipeline design. There is a chance that these sets of instructions will become dependent on one another, reducing the pipeline space. Dependencies arise for a variety of reasons, which we will examine shortly. The dependencies in the pipeline are referred to as hazards since they put the execution at risk. There are 3 types of pipelining hazards. Let's discuss structural hazards. When 2 different instructions access the same resource in the same stage, this situation is termed as structural hazard. These structural hazards cause stalls in the pipeline. A structural dependency causes a structural hazard in pipelining. This dependency occurs due to resource conflict. A resource may be a memory or register or a functional unit like ALU in the CPU. In simple words, when different instructions collide while trying to access the same resource in the same segment of the pipeline, it causes a structural hazard. Here's another way to represent the stall. For dealing with structural hazards, we could stall, use pipeline hardware resources, or replicate the resource. Here are some examples of structural hazards. For cost-saving reasons, a CPU may be designed with a single interface to memory. This interface is always used during IF. It is also used during MEM for load or store operations. When load or store gets to the MEM stage, the instruction in the IF stage must be stalled. Floating points also cause structural hazards. Since many floating point instructions require many cycles, it's easy for them to interfere with each other.
Now we are going to take a look into the data hazards of pipelining. Data hazards occur when an instruction depends on the result of previous instruction and that result of instruction has not yet been computed. Whenever 2 different instructions use the same storage, the location must appear as if it is executed in sequential order. There are 4 types of data dependencies, namely read after write, write after read, write after write, and read after read. These are explained as follows. Number 1. Read after write. It is also known as true dependency or flow dependency. It occurs when the value produced by an instruction is required by a subsequent instruction. Number 2. Write after read. It is also known as anti-dependency. These hazards occur when the output register of an instruction is used right after read by a previous instruction. Number 3. Write after write. It is also known as output dependency. These hazards occur when the output register of an instruction is used for write after written by previous instruction. For dealing with data hazards in pipelining, we use stall insertion. It inserts one or more installs into the pipeline which delay the execution of the current instruction until the required operand is written to the register file. But this method decreases pipeline efficiency and throughput. Another method that can be used is forwarding. It adds special circuitry to the pipeline. This method works because it takes less time for the required values to travel through a wire than it does for a pipeline segment to compute its result. There are some instances where hazards occur even with forwarding. This is a different representation of the stall.
Branch hazards are caused by the branch instructions and are known as control hazards. The flow of program is controlled by the branch instruction. In the higher languages, condition statements are used for the repetitive loops or condition testings. These are converted into the branch instruction variation. As a result, when the decision to execute one instruction is reliant on another result instruction, such as conditional branch, which examines the condition consequent value, a control hazards develop. Here are some solutions for this control hazards: stall, prediction, and dynamic branch prediction. The ideal speedup from a pipeline is equal to the number of stages in the pipeline. However, this happens only if the pipeline stages are in equal lengths. Splitting a 40 ns operation into 5 stages, each 8 ns long, will result a 5x speedup. Splitting up the same operation into 5 stages, 4 of which are 7.5 ns long and 1 of which is 10 ns long, will result in 4x speedup. The compiler can program what it thinks the branch direction will be. Here are the results when it does so.
Pipelining is a rather difficult process. Designing of the pipeline processor is complex. Instruction latency increases the pipeline processors. The throughput of a pipeline processor is difficult to predict. The longer the pipeline, worse the problems of hazard for branch instructions. Interrupts like power failing, arithmetic overflow, I/O device request, OS call, page fault cause a lot of trouble. Here are the various problems in each stage. First, IF. Page fault on instruction fetch, misaligned memory access, memory protection violation. Second, ID. Undefined or illegal opcode. Third, EX. Arithmetic interrupt. Fourth, MEM. Page fault on data fetch, misaligned memory access, memory protection violation. Solutions include interrupting status vector per instruction, deferring check until last stage, then killing stage update if exception and interrupting ASAP, then restarting everything that is incomplete. Complex addressing modes and instruction. Address modes. Auto increment causes register changes during instruction execution. Register state needs to be restored in case of interrupts. Add WAR and WAW hazards since writes are no longer the last stage. Memory move instructions. It must be able to handle multiple page faults.
Handling multi-cycle operations. It is not practical to require floating point operations to finish in one cycle or even two. Doing so would require a slow clock or enormous amounts of logic. Instead, we allow a longer latency for floating point operations. It is common to have several floating point units, that is, floating point adder, floating point divider. Each of these may take multiple clocks per operation. If they are not pipelined, structural hazards can occur. One possible way to implement a floating pipeline is to allow the X stage to repeat as many times as necessary. It is possible to pipeline the floating point execution unit so it can initiate new instructions without waiting full latency. Summary: structural hazards need more hardware resources. Data hazards need forwarding compiler scheduling. Control hazards, early evaluation and PC, delayed branch prediction. Increasing length of pipe increases impact of hazards. Pipelining helps instruction bandwidth, not latency. Interrupts instruction sets and floating point makes pipelining harder. Compilers reduce cost of data and control hazards.
This video is presented by the students of Group 9, Batch 3 from Division R.